This summer, I tackled an innovative machine learning approach to network bandwidth prediction for video streaming. I was employed by Apple's streaming media team to investigate whether machine learning could be a feasible approach to bandwidth prediction, and whether we could leverage it in place of complicated heuristics to both improve algorithmic performance and code readability. As an overview of what I'll be covering today, first I'll go into some background to explain how streaming works with the current prediction paradigm. The main focus will be the innovation of my project, which was highly iterative and data-driven. I took a three-pronged approach, exploring and collecting data, using this data to refine models, and then importing these models into first an internal application for refinement and ultimately into the streaming daemon itself. I'll then discuss conclusions from this experimental approach, takeaways from the internship, and my technical growth over the course of the project. The HLS protocol is a paradigm which provides a continuous streaming experience by allowing the client to download different quality video segments on the order of seconds into a buffer for playback. The available qualities of video streams are listed in the master playlist. The client is then responsible for selecting which tier they would like to stream and for making the switching decision between the quality levels. The network bandwidth is the most important factor for making a decision. If the connection is fast, we want to select a high quality, but if the bandwidth is limited, then we should limit the file size as well so we never run out of the buffer and stall. For this reason, predicting what the network bandwidth will be is one of the most important problems in media streaming. Most bandwidth prediction paradigms use only the previously observed bandwidth to predict what the next observed bandwidth will be. This provides a bit of a delayed reaction. When the network bandwidth changes, the prediction paradigm has to retroactively register this change and adapt. So the major drawback of the current paradigm is that it doesn't have the information to proactively predict when the network bandwidth varies. We want to make a more proactive choice for an even faster prediction. Machine learning fixes all this. We can replace the old heuristic model with a machine learning approach, which can consider all sorts of new on-device features that may be predictive of network bandwidth without having to introduce heavy new heuristic checks into the code. After training extensively on network conditions, our deep learning model automatically selects out features of importance and weighs these more heavily when making a prediction. The streaming case is pretty unique in that for every prediction, we get an immediate answer of whether or not the prediction was correct when we download the segment. So online learning can be leveraged to instantaneously compare the expected versus actual throughput and make the model adapt over time. Even as the model learns, we expect that different features might be the most important features for prediction in different use cases. For example, someone who streams on their TV in a static scenario would have vastly different weighted features than someone who streams on the go using a cellular connection. On-device learning allows personalization of a user's model without their data ever leaving their device, ensuring total privacy and providing an even better bandwidth predictions for a specific user. And this is awesome because we can leverage the newest functionality of Core ML3, on-device learning, in a super applicable scenario. So now the question becomes, how do we do this? As I mentioned previously, the current prediction paradigm uses only historical latency and throughput to make the new prediction. But I did some background research and found all of these features, which have been shown in different cases to impact the network bandwidth. Note that without machine learning, there would be no way to introduce all these features into the prediction algorithm. But with an ML approach, we can put them all into a feature vector and then let the model decide which features to weigh the most heavily. In order to hook these features into a mobile application, I use many frameworks, SPIs, and other sources which report these features through callbacks and protocols. I decided to build out a data collection app which mimics streaming using NSURL session downloads for a static video clip. This is my application. It constantly performs NSURL session background download tasks and reports the networking conditions at the beginning of the download, along with the reported network bandwidth over the course of the download. It also has some cool features which support interactively viewing model performance and online learning. In the data collection phase of my project, it soon became apparent that Wi-Fi and cellular cases would learn very different predictors, so I decided to examine these two cases using transit from Cupertino to San Francisco and switching between Wi-Fi networks at my office. In the transit case, you can see a lot of variation based on location, with areas of low and high bandwidth. In the Wi-Fi case, though, location didn't matter nearly as much, whereas values which measure network connectivity and noise mattered much more. I used the data collection from these runs to build out several different model architectures in Python using Keras and Jupyter notebooks. I decided to start with a neural network architecture because it's highly adaptable and fully implementable with Core ML3. I found that the long short-term memory architecture is really performant, especially when coupled with a custom loss function and optimizer. This was a highly iterative process, where I collected data, trained models off the device, then imported them back onto the device to make a prediction. I trained 7 models off device, validated them by splitting the training data into train and test sets, and then ported them back onto the device to make predictions on new data. Here's how the theoretical model performed when making the switch between cellular and Wi-Fi. As you can see, it picks up transitions really well. However, since this model was trained off-device in a slightly different setting, it doesn't quite predict the throughput correctly for the first case. This is what online learning can fix. Just as I did with the model prototyping, I was able to take online learning off the device and simulate it using Python and Jupyter. Here's how I approach simulating on-device learning. I take feature vectors and ground truth throughputs in batches of 10 and make a prediction on these 10 features. I then compare to the ground truth, compute the loss, and update the model weights. Here's what that looks like for 3 sessions with different network conditions that have been appended together to simulate the network changing. As you can see, it's a bit slow to learn the new network conditions for the switch from a low to a high bandwidth. However, when switching back down, it's much faster to pick up the trend because it's already learned the conditions which contribute to the lower bandwidth. Then, when we introduce an entirely new dataset from the same user, we can see that the model performs very well. It has learned the user's network conditions and can make that proactive quality decision. The final deliverable involves setting up an updatable model on device, and so I created this visualization tool in my application to see how well it does. You can see that the model before training was predicting way off, since it was trained on completely different network conditions. However, after training, it does predict pretty well. I'll close with some key takeaways from this experience. This was my first exposure to an exploratory data science project, and I really enjoyed it. The biggest thing I learned is to not get too attached to your models. You have to keep a really critical mindset and look for the edge cases, continuing to iterate until the model exhibits the desired behavior. I also learned and used a ton of new tools, which will certainly be useful going forward in computer science and data science. This project has a ton of potential impact. If you're streaming this video right now, it's likely that an ML approach to predicting your network bandwidth based on your environment and habits could be used to make this very experience smoother. Beyond streaming, predicting what the network bandwidth will be is useful whenever a network is used to transfer pretty much any kind of data. Just off the top of my head, some examples include sending and receiving messages, participating in conference calls, and performing HTTP requests. Doing so in a way that maintains absolute user privacy is crucial, especially as concern rises about just who has access to personal data. Thank you for listening. I'm really proud to have created such a successful model while simultaneously learning the ropes of ML design, and I hope you learned something in watching.